In this video, I would like to take some of the ideas that we've learned and use them to revisit conductors, and we'll be able to figure out some rules about the ways that conductors behave. Okay, so remember that the defining feature of conductors is that charges can move around freely. That's in contrast to insulators, where the charges stay where you put them. And so, because charges can move around freely, if we put some excess charges on a conductor, the charges want to move as far apart as possible. Okay. And the reason for that is because if the charges repel each other and they're able to move freely, then they will just move as far apart as they can. All right, so that leads to two possible kinds of behaviors that you might expect for a conductor with some excess charge on it. So one is, let's say we have a conductor like this. Maybe the charges will spread out as evenly as they possibly can through the whole amount of material so that the average distance between them is as big as it can possibly be. Or maybe what happens is the charges are going to just keep moving as far away as they can, and they will all end up on the outer surface. Okay, and I think that at this point there's not a lot of reason to have a strong feeling one way or the other, whether the charges will spread out as far as they can to the surface or whether they'll spread out as far as they can and fill up the whole volume. Okay, but we will actually be able to answer this question. Okay, so first, let me make a claim. Okay, so my claim is that inside a conductor, under static conditions, the electric field is zero. Okay, so there are two different ways to justify this claim. So the first is the one that your textbook uses. And basically what it says is that if the electric field were not zero, then any charges in the conductor would experience a force from that electric field. And because the charges are free to move and they experience a force, then the charges will move. And if the charges are moving, it is not static. All right, so in some ways, I think that's not a very satisfactory explanation. Essentially, I'm just saying, well, if I want nothing to be moving, then nothing is moving. There's, I think, a little more meaningful reason behind this. So the way that I like to think about it is, let's say that we have a conductor like this. And let's say that there is some external electric field that is inside the conductor. So not caused by charges in the conductor, but caused by something else in the environment. So there's some electric field that's not zero. But remember, the conductor is made up of an enormous number of positive and negative charges. So if there are some positive and negative charges throughout the conductor, which there are, then the positive charges are going to experience a force in the same direction as that electric field. And the negative charges are going to experience a force the opposite direction. So then what ends up happening is those charges will move in response to that electric field. and you'll end up with this external electric field. But you'll end up with a buildup of positive charges over here and a buildup of negative charges over here, because that's where they're being pushed by that electric field. And then those charges will have a electric field that counterbalances that external field. And the charges will just keep on moving until they have totally canceled out that electric field. There's no reason they would ever stop until the field is zero. Okay, so the other way to think about why the electric field is zero in a conductor is that charges would move until the field becomes zero. That's, the behavior that conductors undergo. Okay, so we can use that information then, that the electric field is zero inside a conductor, to determine where the charges inside the conductor go. Okay, so let's go back to the two cases. We had one where the charges were spread out uniformly throughout the conductor, and one where they all moved to the surface. Okay, so let me draw a Gaussian surface just inside the conductor. Okay, so here's my Gaussian surface on this one, and here is my Gaussian surface on this one. Okay, imagining that it's just inside the surface. Okay, well, in the left-hand picture, the charged enclosed is not zero. Okay, there's some charge that's enclosed by that surface, which means that the electric field inside is not zero. And it can't be zero because it needs to make the flux not be zero. Okay, so this violates my rule that the electric field inside the conductor needs to be zero. Okay, what about in the other case? Well, here we have Q enclosed equals zero. All right, because all of the charge has moved to the surface. So if I draw the Gaussian surface just inside that, then we have no charge enclosed. And if there's no charge enclosed, then the flux equals zero, and that also means that it's at least possible that the electric field equals zero. All right, so the fact that the electric field needs to be zero inside a conductor, and in combination with Gauss's law, tells us that all of the charge inside a conductor needs to move to the surface. Okay. There's one more conductor rule that I want to talk about briefly, and that one is what the electric field looks like outside the surface. Okay, so let's say that I have a situation where I have some excess charges on a conductor like this. And we now know that they all go to the surface. And let's suppose that the electric field outside the conductor looked kind of like this. Okay. Well, I could break that electric field into two components. I could have a component that is perpendicular and a component that is parallel to the surface. And the exact same argument that I made earlier for the component that's parallel to the surface, or rather, the argument I made earlier for the electric field inside will also work for the component parallel to the surface. So if there is electric field parallel to the surface, then charges would move in response to it. Okay, in which case, first, that would violate the claim that the conductor is under static conditions. And second, those charges would keep moving until it canceled out that parallel component. Okay, so the conclusion then is that the electric field is perpendicular to the surface outside a conductor. Okay, so now we have three rules for conductors. Okay, so the first rule is that the electric field equals 0 inside a conductor. The second rule is that the electric field is perpendicular outside the conductor. And the third rule is that any excess charge moves to the surface. Later we will have an additional rule that we'll add, but these three rules are going to determine most of the behavior of conductors.